Hello and welcome to this video on the Java garbage collector. This is going to be quite a heavy video, so sit back and get ready for this one because you're going to basically have to do a lot of research even to fully understand the garbage collector. There's so many things that come together, and sometimes it can come across as a bit ambiguous. But anyways, nevertheless, let's jump in. First things first. What is the garbage collector? So in previous videos we talked about the stack and the heap and how we would have like a reference pointing to the heap, which would originally be on the stack. But the garbage collector cleans up like objects that are no longer in use or no longer available from a reference point, such objects that we can no longer reach. It does this in many ways. There's staging steps, there's things that we'll be going over, such as the young and the old generation of objects. Right now, we're just going to have a look at a high level what a garbage collector is. If you're from a C background, you'll probably understand this a lot better than most people because you've been allocated and deallocated memory manually. In Java, the process is done. The deallocation process, deallocating process even, is done by the garbage collector, so it's fully automatic, which is really nice. This is done by a scanner, which is basically just scans for objects. It looks at the heap memory, identifies which objects are and are not in use, and then it will delete unused objects or unreferenced objects that are no longer reachable. The heap and the garbage collector parts, well, key parts of the JVM, and I think in my video I talked a little about the garbage collector when I was talking about the JVM, the Java runtime environment, and then the JIT. I think that's a few videos back, but that's worth a watch if you want to learn more about this type of stuff. So first things first, here we have like two demonstrations as to how Java works when it comes to picking up objects. Firstly, we have the before marking, and then after we have after marking. All the ones in dark blue are the live objects, and the ones in red are the unreferenced ones. So first, what the garbage collector actually does, it'll look at the object stack to see what objects on the actual heap itself, which it can no longer find a reference to. All these objects are no longer in use or they're unreferenced, and then it will mark those ones as unreferenced objects. And then it comes, this is another process actually called normal deletion. So normal deletion just basically removes unreferenced objects, and basically just frees them up so we can have like pointers to, so we've got some free space. But as you can see, it's kind of fragmented. There's no real linear order in this case. They're all just scattered out, these live objects which are in dark blue. So it's basically the memory allocator is just holding a list of references to free spaces, and even though these spaces are free, think how this is working. It's going to have to go through and scan for these free spaces. So if we basically got an indication as to if it was possible, like when you defrag your computer, we're taking away the fragmentation and we're somewhat stacking, I don't know, in this case, in this particular case, objects. So in this case we're stacking objects, and we want it so we can just find these objects like on top of each other. So it'll go ahead, it searches for free memory, and then it allocates, it tells it, it leaves like a reference to say, look, we've got these free spots after normal deletion. But this is still, well, in my view and many people's view, it's not that optimized, and there's a better way to do this, which we'll go into next. But yeah, the memory allocator, as it says here, holds references to blocks of free space where new objects can be allocated. This is a better way to do it. Deletion with compacting. So as you can see here, it's no longer fragmented. We've basically done a deletion with compacting. So it is possible to increase performance by clustering the remaining live objects. Basically, like I said, stack them together, move them together, whatever you want to call it. It's pretty much the same thing. It makes memory allocation easier and faster, which is a lot better because we don't want to be holding up the garbage collector, because we obviously want our projects to be fast as possible. So memory allocation holds the reference to beginning of the free space, and then this is allocated sequentially. So great way to improve performance, a lot better than just normal deletion. So coming on to this here, as you can see this little graph here, we can see that the minor collections of the objects start really high. We have a ton of objects that maybe are unreferenced or unreachable, and then you can see it kind of just fades down until you get to like the major collections, where these are just stuff like classes and vital things that we actually do need, and we cannot get rid of these. These are stored in the permanent storage of the garbage collector. So having to mark and compact all the objects in the JVM is, a bit inefficient, but it works better than just normal deletion. So as more and more objects are allocated, the list of objects grows and grows and grows and grows to longer and longer wait times and garbage collection times, which can hold your program up, which is not good. So some smart people came up with a way to analyze like these certain applications, and as you can see here, the minor collections, major collections, we start off with a high object count, and then eventually we have fewer and fewer objects remain allocated over time, which is very efficient. So at the start of the video, I spoke about JVM generations and how the hotspot heap structure works. You can see here we have like young generation, old generation, and permanent generation. We have the Eden, then the SO, then S1. We have the survivor space, which is within the young generation, and obviously we have the old generation, permanent generation, where the classes are stored. So the heap is broken up into smaller parts or generations, which is useful for storing objects and how long they're going to be living. It enhances the performance of the JVM itself. So moving on to the young generation. The young generation is basically where all new objects are allocated. So if you remember on that graph, you'll see when it goes high, these are all the young generation objects. So it fills up, causes a minor garbage collection. Minor collections, can be optimized, assuming a high object mortality rate, which is good, and that's why on that graph it lowers out eventually, so we can keep the optimization as high as possible. So a young generation full of dead objects is collected very quickly. Again, referencing this graph, they're collected very quickly, which is nice. Some surviving objects, ones that we're still using, get aged and eventually move on to the old generation, and stuff like, again, classes are in the permanent generation, but these are exceptions to this. So all minor garbage collections are stop the world events. This basically means all application threads are stopped until that process completes. Minor garbage collections are always stop the world events, and that's quite crucial. So let's clean up these objects as quick as possible. So when objects disappear from this area, we say a minor GC has happened, a minor garbage collection has occurred, basically. The old generation is used to store long surviving objects, does basically what it says in the tin. Now these three structures what are within the heap, the generations, it kind of just makes sense. Used to store long surviving objects, unreachable objects. Typically, threshold set for the young generation, and when that age is met, the object gets moved to the old generation. Eventually, the old generation needs to be collected, so this is collected on a major garbage collection. Major garbage collection is also stop the world events, so often a major collection is slower because it involves all the live objects, so it's got to go through each one of them. So for responsive applications, major garbage collection should be minimized. So we have to kind of kill those objects we're not using to begin with at the start to prevent having so many objects in the old generation. The length of stop world event for a major garbage collection is affected by the kind of garbage collector that is used for the old generation space. Permanent generation contains metadata required by the JVM to describe the classes and methods used in the application. The permanent generation is populated by the JVM at runtime based on classes in use by the application. So, in addition to this, Java SE library classes and methods may be stored here. Classes get collected, unloaded if the JVM finds they're no longer needed, and space may be needed for other classes that potentially get loaded here on out. So you could think of this as a database class that gets loaded. So if we find a class that's not being used and we want to load in a database class, when we're calling a particular method for that matter, it may clean up some classes, put in this database class. The permanent generation is included in a full garbage collection. Definitions, these are very important. I've got references to everything that is in this particular key keynote, so definitely go ahead and look them up, because half of this is very very hard to understand, and even some of this stuff for me myself I've had to reference and look up just to make sure I got all the definitions and whatever else correct, because some of this stuff is hard to remember when on a daily basis you're not actually even working with a garbage collector. You're not doing, well, you are working with a garbage collector in a sense, you just don't know what's happening behind the scenes. So for Hotspot JVM, the memory pools for serial garbage collections are as follows. Eden space, we kind of went over that, the pool from which memory is initially allocated for most objects. The survivor space, again, it's on the heap. The pool contains, this is in the young generation, the Eden and the survivor space. The pool contains objects that have been, they've survived that particular garbage collection from the Eden space. And then we move on to the tenure generation, the pool containing objects that have existed for some time in the survivor space. Permanent generation, non-heap, we have to remember that. The pool containing all the reflective data of the virtual machine itself, such as the class and method objects. With Java VMs that use class data sharing, this generation is divided up into read and write areas of access. So code cache, non-heap again. The Java Hotspot JVM also includes a code cache containing memory that is used for compilation and storage of native code. So yeah, kind of maybe screenshot this bit for the definitions. It's going to be very useful if someone asks you about the garbage collector. Important thing to remember, this is a great quote I found on Stack Overflow. So this seems like a common misunderstanding. In Oracle's JVM, the permanent generation is not part of the heap, as we got here. It's a separate space for class definitions and related data. In Java 6 and earlier, intern strings were also stored in the permanent generation. In Java 7, intern strings are stored in the main object heap. So, storing Java classes. Java classes are stored in the permanent generations, I've kind of mentioned a few times. The basic fields of a Java class there are methods, names, constant pull informations like data read from a class file, object arrays and type arrays associated with a class, an object array containing references to methods, internal objects created by the JVM, information used for the optimization of the compilers, JITs. Again, there's a video on that a few back from this. Again, take a look if it's something if you are interested in. Visual overview of the allocation. So we get the allocations in the young generation, we get the promotion to the old generation, and then the permanent generation. Going back over object allocation, so here what we have is we have the early stages of the Eden. So this should basically actually, this is just the young generation what we're looking at. So we get it allocated before it's marked, even though we could have more in here. So we put these from the survivor space to the survivor space. So any new objects allocated to the Eden space, both survivor spaces start empty. So fill in the Eden space. Let's have a look here. We have the just allocated, then it'll be created in the Eden space. We have the SO survivor space and S1 survivor space. So we have the 3 and the 1 in there. These are just objects, all live objects. And then we come to copy and reference objects. So we have all these unreferenced objects in the Eden space, and we have one or two reference objects. Reference objects are moved firstly to the survivor space. So we've got one in there already, then we're going to add another in. Unreferenced objects are deleted when the Eden space is cleared. So once it gets cleared, we'll get rid of these unreferenced objects, and we'll have that one we have one already in the survivor space and one also in the Eden space, so we're going to have to move that to the reference, the survivor space, which is S0 in this case. So object aging, again we've got a diagram. These diagrams could get confusing, but at the next minor garbage collection, the same thing happens for the Eden space. Unreferenced objects are deleted. And basically, with reference objects, these particular reference objects are moved to a survivor space. However, in this case, they move to the second survivor space, which is S1. In addition, objects from the last minor garbage collection on the first survivor space, S0, have their age incremented and get moved to S1. So once all surviving objects have been moved to S1, both S0 and Eden are cleared. So notice we have differently aged objects in the survivor space. We have the 1111 and we have the 2211. We're going to be clearing this up. This is just showing you the flow of the object aging. Additional aging here, we have, again, we're talking about, we've got, 3, 3, 2, 1. Some of these, this is just like an incremental process for the aging. It's kind of similar to this one from the survivor space. We're switching them around. So we've got survivor space on the left, survivor space on the right. You can see here we're from the survivor space to the survivor space, and then to from. Let's not get hooked up too much on this stuff, but it's very important to understand how it works and how long it's been in a survivor space, or how long it's been in a tenure space, or how long it's been in a permanent space. After a minor garbage collection, when age objects reach a certain age threshold, we have like 8 in this example. They're promoted from the old generation, well, the young generation to the old generation, which is tenured. So right now we actually have like the young generation here and the old generation. Remember, the young generation has the survivor spaces, so it can last in there quite a long time depending on when the garbage collector comes around. Allocation here from the young to the old, we have the allocation and it gets promoted up to the young generation. So as minor garbage collections continue to occur, objects will continue to be promoted to the older generation space depending on what's happening with those particular objects. Again, one last process summary for the garbage collection. We get it allocated up at the top, we drop it into the Eden space. We have a bunch of objects in here that are alive. So from the survivor space, we have nothing to the survivor space, we're going to leave them there. But if they're still alive, on the next GC garbage collection, we may push them up to tenured space. Eventually, maybe major garbage collection will be performed on the old generation, which cleans up and compacts that space. Important references, I'll leave these up for just a few more seconds. It's incredibly important to go look at these. They're a lot better than, well, incredibly useful, probably a lot better than what I've explained. These guys on here, very, very intelligent when it comes to Java, and especially the Java garbage collector. There's many more diagrams on there. There's a lot of diagrams that are similar to mine where I had to basically read over these particular diagrams because I haven't gone over the garbage collector in about 3 years. It becomes one of those things you just kind of put to the back of your head unless you're actually working with the heap and changing the size of the heap and things of that nature. But yeah, please do check these out. These are very important references if you want to fully understand this. And there's much more online. Just search Java garbage collector, but from what I come across, these are probably the 3 best links. Again, remember to ask any questions. There's no dumb questions. Everyone has to start somewhere. Even with the garbage collector, it does still confuse me a little bit, but it's starting to make more sense now. Remember to subscribe for my videos, that really helps. And if you have any questions, drop them in the YouTube comment section below, or do follow me on Twitter @CalHadwin. So yeah, thanks for taking time to watch this video, and I shall see you in the next one.